I am I come from the University of Oslo, where I'm the associate professor, and I work with fundamentals for distributed systems. And today I'm going to talk about self-adaptation in autonomous systems, and I hope you enjoy the talk. I came into looking into self-adaptation in the context of autonomous underwater vehicles, and also in the context of digital twins. And today I wanted to show you what we have been doing in this context, and I want to do using some use cases. So in the case of underwater autonomous vehicles, I am going to talk about single AUV, which is able to do inspection of a pipeline that is underwater. And in the case of digital twins, I will do it in, using a use case on greenhouse, which has an automatic watering system. So in the first part of the talk, I will focus on autonomous underwater vehicles, and then later we go into digital twins. Okay. So I am part of this project called Remaro, and Remaro is a Marie Curie educational training network, which is educating 15 PhD students along Europe, and these PhD students are working on reliability for autonomous underwater systems. And part of the motivation of the project is really to take advantage of the blue economy that happens underwater, where it is really difficult or even dangerous for humans to be there. And these robots that can operate into these environments are really needed. And one of the characteristics of these environments is that the communication is really difficult. And therefore, the capacity for a robot to actually work with autonomy takes on to some tasks using some autonomous reasoning is really important. And so the focus of the project was actually these autonomous decisions, and you can actually see in the logo, which is a brain of the robot. And if you want to see what other results are about this project, you can actually go into the web page and check what the other students have been, all the different students have been doing. So in this context, then autonomous systems are systems that design from themselves, what to do and when to do it. And these systems have have this ability to handle knowledge, and to handle knowledge to adapt their behavior in response to changes, internal changes or changes in the environment. And then we can see that really adaptability or self-adaptation is an important characteristic of these systems. And so they can react to uncertainties. What happens if something fails in their states, or there are some changes in the environment that they need to react. Back in 2020, when we started the project, we were looking at actually what was happening into these autonomous underwater vehicles. And at that time, most of the vehicles were actually operated, remotely operated, meaning that there was somebody in a ship on top and an operator really sort of with a cable into these underwater robots, which help with the decision of the robot, what to do in certain circumstances. And nowadays, these robots, and at that time, they were starting to explore or to develop actually these autonomous behaviors. And nowadays, we can see with these Elumi robots, they have this hybrid operation where they can be operate remotely, but they are also able to do some of these autonomous tasks, which are routinary tasks in environments that they actually know. And which means that there is still a lot to do with that in the decisions of these robots, especially when there is a lot of uncertainty. So as part of this, understanding how these autonomous robots work, I was part of development of an exemplar, which was the main work of one of the PhD students in Remaro, Gustavo Silva, a PhD student from Delft. And he was developing this, and we were helping to develop this exemplar. And this exemplar actually has this scenario of pipeline inspection of a single AUV. And the idea is that this the exemplar consists of an AUV able to do two tasks: search for a pipeline, and once that pipeline is found, it starts inspecting the pipeline, like for example, for corrosion or something like that. So during the search of a pipeline, what the AUV does, it starts to deploy like a path that goes like a spiral from this position until it finds the pipeline, and then once it finds the pipeline, start to follow the pipeline. And these are the two tasks that AUV can do in this exemplar. And the exemplar has, the robot in the exemplar has 3 navigation modes, meaning that it can navigate at high altitude, mid altitude, and also low altitude. And the robot changes this navigation depending on the water visibility, meaning that if it is navigating high, and then there is the water visibility is very bad, that cannot see what is happening now in the seabed, then it needs to move down. And which means that, when it is up and the water visibility is good, it has a bit more spectrum to see, so it has more chances to actually find the pipeline faster. And when it goes down, then it has this view spectrum is shorter, which means it takes more time. But it has to change depending on what a robot can see, right? Underwater. And this is actually an uncertainty which triggers the configuration in the exemplar. And the other uncertainty is about thruster failures. So thrusters are these components in underwater robots, which helps with the stability of the robot for when it is moving, when it is navigating. And when the robot is have some failures in these thrusters, it has, it starts, it has the trajectory, with a planned trajectory, it starts deviating. So the location that is calculated starts deviating. So it might need to, change to different controllers that works with less numbers of thrusters, so that they can actually calibrate the location again. So these are the two uncertainties that the exemplar can handle. And if we look into the architecture of the exemplar, so the exemplar has this an architecture with 2 layers, where in the managed subsystem we have really the different functionalities of the AUV. And it has an external layer which handles the self-adaptation loop. And if we look closer into the self-adaptation loop, it follows this MAPK, where basically in the exemplar it monitors the water visibility and also the thrusters. And depending on the quality of the water and also the state of the thrusters, it decides if it needs to change, to reconfigure. And if that is the case, it selects what is the best possible available configuration to reach some requirements of the robot. And once this is selected, then the execute basically deploy the new configuration. And if we look, it is happening, in a loop. The robot is doing this checking all the time. No? And if we look closer into the knowledge of the managing system, the configuration, the adaptation logic of this exemplar, it was built using framework called MetaControl. And MetaControl has knowledge, which is both in a meta model called Thomasis. And this Thomasis meta model, what it does is really captures what is the triggering conditions for the configurations, and also store the different plans that it also has the different plans that is possible to have that the robot can choose. However, when we were sort of looking into the knowledge, we realized that actually how this configuration is entering into the knowledge base is very much ad hoc. So which you really need to know which components can go together, which configurations are valid. And for example, there was no way to putting 2 components together could trigger some failures. So we saw that there was potential to do something in this context for purpose of analysis, right? So we started to actually explore if it was possible to use family-based methods, meaning this is one method inside software product lines, to actually manage the variability, all these different configurations in the self-adaptive systems. And we did it using basically in a use case inspired by the SWAB exemplar. And so if we see a little bit what these family-based methods, it allows you to actually model the variability of a product line. And it allows to capture structural variability, which means all the possible configurations of a product, and also behavioral variability, meaning all the different behaviors that these different products can have. And also, there is a possibility to actually capture what are the, or to model the triggering conditions for product selection. And then we saw that, I mean, this is really has this, similarity with the kind of architecture that we have been seeing in the exemplar. So then we wanted to see what it was possible to see, to do in this context, right? And for, so then we sort of started to see there was already something that was done in the context of using software product lines or in particular family-based analysis in autonomous systems, and we couldn't find anything. And later, actually, once we started to work into this area, we got confirmed that actually dynamic software product lines, which means it's the ability to choose to select different products, is actually a challenge in robotic systems. So this is something that it needs to be, that has not been explored. So we started this work. It was in the context of another PhD student in the Remaro project. It's my PhD student in Oslo. And we were starting to actually explore how this family-based behavioral model analysis can work in the context of autonomous systems. So, and then for capturing, and when we were exploring all these different sort of models that are possible to use in these software product lines, we went for future models to capture the configuration space. And future models basically allow you to organize the configuration space. And it gives you a way to describe what are the valid products in a product line. So for example, in the case of a robot, we have this set of features. We have the robot, which has these different navigations. The navigation modes can go high altitude, mid, and low altitude, right? And it has these two different tasks that can do. Like for example, you search for a pipeline and then follow the pipeline. And you can see that, I mean, in the future models, you can have some mandatory features. So these two things are mandatory for this use case. And you can select only one of these whenever you are in a valid configuration. So really, these feature models allow you to capture what is the configuration space. For capturing the behavior, we're using future transition systems, which is an extension of transition systems that on top give you some guards in the transitions. So that if a product is selected, this means that these guards in the transitions are true. So which means that allows you to actually select different products. And what it does is that you have a big model, which consists of all possible products of a product line. And it's basically a superimposed product, which is called 100% models, and describe the configuration of the whole product line, right? And it has a formalization, which means that once it is modeled, you can actually do some analysis, and you can start asking questions about the model. And if you see sort of closer into what we did in the use case, so we have that the robot starts the task, and then depending on if the future search or follow are selected, for example, it starts searching, and also depending if which navigation mode was selected, for example, low, mid, or high, it's sort of, for example, it is searching high, and this is one configuration that is to execute, no? And our sort of level of abstraction was very small, which means that we say that the robot is staying in a configuration high with some probability, and afterwards it can found the pipeline with some probability. And we can go into some recovery states where it's capturing the trusted failures with some probability. And there is also some external controller, which will activate and deactivate the different features so that we try to trigger self-adaptation, meaning that the robot has to move to a different configuration. So this was how we were capturing self-adaptation. So as I mentioned before, sort of, actually the future transition system is a probabilistic future transition system, which has probabilities, which means that, for example, if you are insertion low, you have some probability to stay there and some probability to actually go to a different state. And then, I mean, if there is some external entity or external automata which cause the robot to move to a different configuration, for example, search method. And for actually capturing self-adaptation or the ability to select different products, we sort of we were using a feature controller, which dynamically activates and deactivates different features. Like, for example, if you are in a search altitude high, you are in a search altitude high because the water visibility is good. And which means at this point you are activating the feature high. But if at some point the water visibility changes, and it changes to a different, maybe average, then you deactivate high and activate med, and then you go into a different water different state, which will trigger reconfiguration or basically in this transition system, we will trigger to the robot to go a different configuration. And for example, if at some point sort of the pipeline is found, then we have a constraint that, I mean, if the pipeline is found, you have to go to low navigation because then you have to go closer to the pipeline, for example, find corrosion. So then you need to go low and then follow the pipeline. So this is how we were sort of modeling the different aspects of a self-adaptive system. And one characteristic is that actually the future controller has to preserve this the different products that is captured in the future model. So this is part of what the future controller is doing. And we also needed to sort of model the environment. In this case, the environment is a probabilistic transition system, which basically changed the water visibility, meaning that we have some current probability, so the current in the water, which generates, some particulars in the water, which really sort of changes the visibility of the water. And we sort of have some way to express how the water visibility can change between the minimum and maximum values, which are basically the parameters of the model. And if you see sort of everything like in a step back, just to see everything, we see that we started really looking into this similarity with this self-adaptive system with the two layers self-adaptive architecture, where basically everything that's basic functionalities of the robot is captured with a probabilistic future guarded transition system. And the self-adaptive layer is captured with this future controller, which is basically preserving the different configurations given in the future model. And we have the environment, which is captured also by a probabilistic transition system. And once we have sort of the model, it's possible to do some analysis. So for analysis, we use the tool Profit, which is a family-based analysis tool, which is built on top of Prism, which is a probabilistic transition system, which is extended with future guarded and with future guards and future controllers, where the future controller actually is also has to preserve the future model. And then it's possible to do some analysis with properties, analysis of properties via probabilistic temporal logic, using, for example, Prism support probabilistic PCTL or probabilistic FTL and some other probabilistic temporal logic languages. And then it's possible to actually do some analysis with some scenarios where we need to deploy where we need to settle the parameters, right? For example, we can imagine two scenarios, a more hostile scenario with a North Sea where we have like water visibility goes between 1 and 10. There is a current probability high, 0.6, so you know the water visibility to change, and a pipeline inspection of images. And we have another scenario, which is a more quiet scenario with the Caribbean Sea, with water visibility between 3 and 20. The current probability of meaning that there is less probability of having bats in the water with a longer pipeline inspection. And it's possible, to start experimenting with these different scenarios. But it is also possible to do some quantitative measures. In this case, the model needs to be enriched with some rewards annotations. For example, energy, like going from search to found takes some energy. Or, for example, time, going from one stage to another takes such amount of time. And once you sort of enrich the model with these rewards annotations, it's possible to have sort of to collect like kind of analysis that says, given, for example, the North or the Caribbean Sea scenario, what are the expected minimum or maximum time or expected minimum or maximum energy? And but this is given a concrete scenario, right? But Profit also allows parametric model checking, which means that instead of asking, does the property holds in this particular environment, we can sort of switch the question and ask for which environments the property holds, right? And in this case, we really open the current probability and we say for which current probabilities certain properties hold. Like, for example, we were calculating like minimum energy for the North Sea star scenario where we opened the current probability. And then we develop a model. We have this model with 3 navigation modes, and we have a different model with 5 navigation modes. And so we wanted to see if actually having more granularity in a number of altitudes makes sense if we take something in the model. And we compare, and actually, this is the results for the 5.1, which is lower than the 1.3. So we saw that at least the model tells us that it makes sense to actually have more fine granularity in a number of levels of navigation. Other kind of analysis that is possible to do with Profit is this Pareto optimal, meaning that you can compare two different rewards annotations or reward structures. Like, for example, what is the best compromise between time and energy consumption? For example, for a specific scenario, the North Sea. So it's possible to have these best points comparing two different reward structures. So if we go one step back, so we can see what we did is really, we wanted to do an assessment of the potential of this family-based analysis method for autonomous systems. And we did that using a small scale evaluation. Basically, it's a single AOV is inspecting a pipeline. And we saw that the pros for this kind of methods is the possibility to manage different configurations. And once you have the model, the systematic analysis of the behaviors of all valid products. So you need to actually go product by product, but you can do the analysis of all the valid products in one. And this is really what it gives you this kind of analysis. Okay. So with that, I want to conclude this first part of my talk. Now I want to show you what we have been doing with self-adaptation in the context of managing lifecycles of assets in digital twins. So what is a digital twin? Probably, I don't know if you have heard about digital twins before. So a digital twin actually consists of a number of components, which is a digital twin, which mimic or mirror some physical components, which are the physical twins. And the digital twin is updated with observations from this physical twin. And as and the digital twin has some ability to actually do some predictive analysis or some informed decisions that actually can have an effect on the physical twin. Okay, and as you can see, really, sort of, before I go into that, there have been a lot of success stories in the context of digital twins. Here are just two. In 2019, General Electric experienced like 5 to 7% increase in the energy production from digitalizing the wind farms. So it was really sort of some success stories. And in Norway, the Johannes Sverdrup oil field actually have a very boost in the earnings of 200 million in 1 year, just by developing this digital twin technology of their platform. So this is really also a hot topic, and where it is possible to actually do something interesting and to have a good impact. And in the area or the domain of digital twins is also self-adaptation is really core in the concept of in what a digital twin is, because we see that actually the digital twin is monitoring the physical system and it can, it's adapting the behavior of the twin, of the physical system. And in that sense, like for example, we have like the digital twin is monitoring the assets that are in the physical twin and update the knowledge about the status of the physical twin. And it can analyze the needs for adaptation using some requirement analysis or some other techniques, and also have a plan for adaptation, how to meet the requirements that you want to have with respect to the physical twin. And after that, execute the plan, which means change the behavior of some controllers, or maybe start some other components, etc. So this really sort of something that which this is also in the one main characteristic in digital twins. But we were trying to see if what about if you want to actually change or adapt the behavior of the adaptive layer. So go one level up and see if you can adapt the behavior of the adaptive layer. And so we were exploring this possibility with some colleagues in Oslo, and maybe Bengo is the professor in the University of Rotterdam. And we took inspiration, so to explain what we did in this work, we took inspiration of another exemplar, which was developed by some colleagues of mine in the University of Oslo. This is actually a master project where some students were building automatic watering system for some basilicum plants. So this is a picture taken from the digital twin lab in the University of Oslo. And so we took inspiration of this project, and we developed our own use case. And in use sensors to measure the moisture of the soil and also the health of the plants. If the leaves are green enough so that the plant's happy somehow. And also that the two pumps, one for water and one for pesticide, in case the plant gets sick. And as part of the digital twin components, we have models of the plants and models of the pumps. Some requirement analyzers, like that sort of there are components that analyze the moisture of the soil, and also some health analysis for the plants, and some controllers that manipulate the pumps. One for the water and one for the pesticide. So this is what we have in the digital twin. So and we wanted to talk about another concept that it is also present in digital twins is this concept of life cycles. Like for example, a pump can be working perfectly, or it can fail. And when it fails, you need to sort of, before it enter into maintenance, it needs to change the controller so that there is a controller that knows that it's working under these conditions. So maybe the valve of the water is not delivering as much water as before. So instead of watering 3 seconds, you need to water 5 seconds because it's not working as before, right? And similarly, there are also sort of change in life cycles, like physical models can evolve. Like, for example, the plant, before we started with a seed and become a baby plant and eventually becomes a big plant. So, and also like the watering routines for these different, cycles of or stage cycles of a plant needs, maybe a big plant needs more water. So you need to water for longer. So you need to do some self-adaptation in that context. And then in this context, I mean, you can see that like the plant, for example, can be involved in different life cycles, and the components that in the digital twins can be also in different life cycles. Like, for example, a plant can be healthy or can be sick, but at the same time, the plant can be maybe a small big plant which is healthy, or it can be a big plant which is sick. So you have this the connection between different life cycles where the digital twin components are parts of in this context. And each life cycle requires different setups. So we need to start different components, or we need to, maybe when the plant is sick, we need to start a component which is managing the pesticide, so that the plant can get some medicines, for example, or something similar. And one question is, like, for example, do we really need to model the whole transition system? So how to go, for example, if we talk about a plant, how to go from a baby plant or to a medium-sized plant, right? And this will be an operational view. So you model actually the transition, how it goes from one side to the other, right? Or instead, we can talk about, can we actually recognize in which stage we are? So instead, we observe, the physical system, and based on this observation, we can decide in which stage we are, which will be a more declarative view. So instead of operational, we kind of observe and decide in which stage we are. And if we see that, if we observe that the physical twin has changed from one stage to a different one, then we need to see if we are okay with the kind of components that we have, or if we need to reconfigure. Okay. So in this context, sort of, as I said, we have an extra layer, which is actually in charge of reconfigure the configuration, the self-adaptive layer, the behavioral self-adaptive layer of the twin. Like, for example, given a sick plant, do I have the right components? Maybe then I need to start a new controller, or maybe I was analyzing the plant for moisture with some requirements, but now that the plant is sick, I need to have a different requirements. So I need to actually shut down that monitor or this analyzer and start a different one, in the case the plant is sick. So what we do is really sort of recognize, monitor the twin, see in which stage we are, and based on that, we check if we are consistent with respect to the kind of stage that the physical twin is. And if it is not in a consistent state, it plans for configuring the adaptation layer. And after that, it executes, meaning that it remove new components, and these components will remove and add new behaviors possible for the behavioral twin. So you can see here, like, for example, if we have a plant which is a mid-sized plant which is sick, it monitors the state of the physical twin, or the state of the plant, and detect that actually this plant is in these two states, right? And then analyze the architectural coherence to see, do I have the right components or I need to change? And then if the case it is that I don't have the right components, then it goes to repair this architectural inconsistency, and then execute a plan and update the knowledge. And this sort of detecting of and if we are in life cycle states which are declarative, what we did is like, how can we actually know in which stage we are, right? And we do that via a membership predicate and a consistency predicate. So the membership predicate, we basically say when an asset is consistent with the states that it is currently, And the consistency predicate basically check which components need to be activated when we are in that stage. And the self-adaptation happens via something called abductive reasoning, which is basically, you can see it as an educated guess. So based on the knowledge that I have, that I know that I have about the physical twin, you do an educated guess. So what are the components that I need to start or to remove in order to be consistent again? So let's see one example. So for example, let's see these declarative stages of a plant which is happy or is healthy or is sick. So then we have that the plant can be sick or can be healthy. And the way that we detect if that the plant is sick or healthy is depending on the membership function and the consistency function. And the membership function for sick is measuring actually this NVDI. It is very interesting actually because it is a measurement that it is using some infrared cameras that has been used actually with satellite pictures of the Amazonas to detect deforestation and to detect the health of the Amazonas. And we were using a sort of similar idea, and actually the master project in Oslo were using actually these infrared cameras to detect the color of the health status of the basilicum plants. So depending on, you can have actually some measurements and decide if the plant is sick or not, and then which means that based on some values you can see if it is less than that, the plant is sick. If it is greater than that, then the plant is healthy. So then we were using these NVDI values to detect membership of the plant. And for the consistency, we can see that these are the requirement analyzers that actually check the moisture of the are checking the moisture of the soil. And in the case that, for example, the plant is sick, you need different moisture conditions that in the case the plant is healthy. So for when the plant is sick, you need to have a moisture of less than 5. And for when the plant is healthy, then you have less than 10. And then imagine that you have a healthy plant, so the stage is healthy, and analysis of a digital twin tells you that actually the state is the plant is healthy. So and the requirement analyzer that you have deployed currently is is this one. So you see that it's actually consistent with what you have. So adaptation is not needed. But suddenly the plant gets sick, right? And this component is still running. You detect actually that the plant is sick. This component is running, so there is inconsistency with the architecture, the current architecture that you have. So then you need to do some adaptation. So in this context, then you see, okay, what is missing? And in this case, what it is missing is this, requirement analyzer for plants that are sick. And we need to remove this one, no? And then you execute the repair of the configuration. And after you repair the architectural configuration of the twin, then you have the new requirement analyzer as this. And that is how we sort of manage declarative reconfiguration of the stages. So we have an implementation using semantic technology for these declarative stages, where basically the monitor collects data about the digital twin, and then have this staff operation, which actually have this classification of the physical twin according to the different declarative stages. And based on this tagging operation, then it does some queries for consistency to check if you have the right components for the digital twin. And in case you don't have the right components, then if there is inconsistency, then you go into planning how to repair the architecture of the current digital twin. And once you decide what is the plan, then you do the reparation and execute, which means you update what it is in the knowledge, which components you have now available, and also which components you need to start and shut down in the digital twin. So this is all for today. So basically, I have shown you this how we have been exploring self-adaptation in the context of two application domains: autonomous underwater robots and also digital twins. And I have been showing you what we have been doing using two use cases. Basically, a single AUV inspecting the pipeline, and also automatic reconfiguration of digital twin components in a context of a smart greenhouse. And in the context of AUVs, we have been exploring this family-based behavioral model and analysis with a two-layer system, right? Where we have basically the domain concerns are done via probabilistic future transition system, and the adaptation layer is done via future controller, and the environment is also doing via a probabilistic transition system. And we have also shown which kind of analysis is possible to do once you have the whole configuration in one big model that you can analyze the whole family of products in once, right? And in the context of digital twins, I have shown you how to think about these different life cycles in the context of, instead of being operational, we go to declarative stages. So instead of modeling what are the transitions to go from one life cycle to the next one, or one stage to the next one, you actually detect or declare what are the conditions so that you know in which stage you are. So using declarative stages. And in this context, we have explored self-adaptation with 3 layers, with an external layer that can actually manage reconfiguration of the adaptive behavioral layer. So this is all for today. Thank you very much.
Thank you.